Hello and welcome to the second session of waveguide. In the previous session, we have discussed about the basic concepts of TE, TM and TEM mode. And also we have discussed about the EM spectrum bands followed by advantage and applications. So in this session, we're going to understand the derivation part of wave equation and the fields of wave equation, that is finding Ex, Ey, Hx and Hy in terms of Ez and Hz. So let us start the first wave derivation, that is wave equation. In wave equation, our main goal is to find the relation between del square E and E or del square H and H. Here E and H is an electric field and magnetic field. So once we got these two derivation, then we can say that this is an wave equation, and sometimes it's also called as Helmholtz equation. So let us begin this two derivation part from the basics. So let us start the first introduction about the wave equation. So for finding the wave equation, we should know the electric field. So here the electric field can be given by magnitude with certain signal. Here the signal is complex exponential signal, which is a time dependency. So sometimes it is called as time varying field also. So once you understand about the time varying, then we can apply to this one to the Maxwell's equation. So the main idea behind is that applying a partial differentiation with respect to time to the electric field. So here we are going to apply 2 times partial differentiation with respect to time with the electric field. The first partial differentiation field will give the relation between dou by dou t is equal to j omega. The second partial differentiation will give the relation between dou square by dou t square is equal to minus omega square. So let us start how exactly we can obtain this equation. So as we know that this is our electric field, we have to apply the partial differentiation. So once you apply the partial differentiation, the constants can be removed outside, and we know that the partial differentiation of e power of j omega t is nothing but constant times of the same signal into another constant E naught. So as we know that E naught into e power of j omega t is nothing but your electric field. So replace with this one with electric field. Here the point can be noticed here is that once we have equality, then I can say that if this is equal, then this should also equal. So dou by dou t is equal to j omega, and that is we got the conclusion. Again you have to do a partial differentiation for second time, then we're going to obtain the relation between del square dt square is equal to minus omega square. So I can say that you have to concentrate 1, then 2, then 3. Then we have to apply a 4 Maxwell's equation, which is a time varying field. So as we know that the 4 Maxwell equation, I don't want to discuss much about that. So let us begin with the first Maxwell equation. And one more thing I want to tell you that we are going to take a 2 assumption, that is conductivity is 0 and the volume charge density is 0. This is because of medium is assumed as free space. So once you observe it's a free space, then you have to apply this to condition. Now let us start with the first Maxwell equation. In first Maxwell equation, we know that del cross H is equal to Jc plus Jd. As we know that Jc is equal to sigma E, as the condition is taken as sigma equal to 0, then Jc also 0. So this term is get vanished, then the remaining term is del cross H is equal to Jd. As we know that Jd is equal to dou by dou t into d, and we know that d is equal to magnetic flux density. The magnetic flux density is given as d is equal to epsilon E. So now what we have to do here is that this d should be substituted over here. So now we can say that the constant is removed outside and remaining terms can be applied to the electric field. Now we can observe the three term. One is epsilon, one is dou by dou t is nothing but j omega as we have discussed previously, and remaining E. So now this term can be written in this fashion. So once you obtain the JD, the same thing can be substituted over here or here, then we can say that del cross H is equal to JD, that is nothing but this one. So we got Maxwell first equation and we got some conclusion. Now the same thing we have to apply for the second Maxwell equation. Again we are going to get some conclusion. In second Maxwell equation, what we have done here is that del cross E is equal to minus dou B by dou T. So what is B stands for? B stands for magnetic flux density. So B is nothing but mu H, where mu is again a constant that can be removed outside, and the partial differentiation can be applied to H. Now again we have three terms. One is mu, another is dou by dou T, again can it is written as j omega, and H. So now from the second Maxwell equation we got another conclusion which is written as B. So let us apply a vector calculus to the above equation. So we are going to apply a curl on both left side and right side. So we are going to apply here the curl left side and right side. So once we apply the curl, then we have to follow the vector calculus equation. So in vector calculus we know that del cross of E is nothing but del dot del E minus del square E is equal to the right side part. So the right side part is minus j omega mu into del cross H. So as we know that the del cross H is epsilon j omega E. So now we can substitute the del cross H as epsilon j omega E. So now we can observe that j into j is j square becomes minus 1 becomes plus. So now I can say that the remaining term is omega square mu epsilon E. So we can get the conclusion that del dot del E minus del square E is nothing but omega square mu epsilon E, what we have derived. Now let us continue with the Maxwell fourth equation. Del dot D is equal to rho V. As already I have discussed that rho V is a charge density in the free space, the value is 0. So we have substituted it as 0. Now the term D is epsilon E. As already I have discussed that epsilon E is a constant. Now the remaining term becomes 0. Means what I mean to say that epsilon has a certain value, but del dot E should become 0 to balance this equation. Now del dot E is 0 from the conclusion of Maxwell 4. So this del dot E can be substituted over here. Then we can get del square E is equal to omega square mu epsilon E. This can be rewritten as del square E is equal to minus omega square mu epsilon E, as negative can be substituted over here. So from here we can get the conclusion that the electric field, whatever we have derived, can be applied to magnetic field also. Yes, you can write similarly that E replaced with H, remaining constants as usual, but here again the E can be resubstituted as H. So we are not showing much interest in solving this derivation. So once you got these two equation, then we can say that this is a wave equation, and sometimes it is called as Helmholtz equation. I hope you have understood. For the revision part, I want to give a clear instruction for your exam point of view that try to remember the electric field, then go for 2 times partial differentiation, apply the 4 Maxwell equation, taking the condition as free space as a medium. So substitute over the conditions and try to get this 2 equation. I hope you have understood. So now let us go for the third part derivation. In third part derivation, as already I told that this is a rectangular waveguide and we are allowing the wave to go in z direction. So what is this one? This is a wave equation. So whatever we have done, that is a wave equation. Now here del square E and del square H has to propagate in z direction. Now this two equation can be rewritten as in this fashion. Try to observe the above derivation that here we have not written z because we are not told that that wave is propagating in z, but here we are telling that the wave should propagate in z. For that we have written the suffix z, and nothing much explanation is needed over here. Now as we already discussed that we are going to concentrate on electric field, similarly we are going to write for magnetic field. So now again I have taken here as electric field as a reference in the z direction. Now let us start the mathematical calculation. The Laplace operator del square can be written in this fashion, as you know already. So what I have done is that this Laplace equation is substituted over here. Then this is nothing but your Laplace equation with Ez, or Laplace operator into z. So now this is a left hand side can be written in this way, the right hand side can be written as it is. Now one more condition we have to take is that dou square by dou z square is equal to gamma square is nothing but propagation constant, where gamma is known as propagation constant. So we have to substitute over here. We have substituted into Ez, the same thing, yes. Because of less space, I have written here Ez, and now this Laplace operator into Ez is nothing but your right hand side. So what I have done is that I have multiplied Ez into the Laplacian operator, then uh, then remaining term is written here. So what I have done is that I have taken this part to the left side, then I can say that this in this part Ez is taken common. So whatever we have written here, this is nothing but h square. This is treated as h square. So now h square is nothing but this part. You substitute the h square over there, over here, then we can get this equation. Now I can say that this is nothing but electric field equation. Similarly, we can go for magnetic field equation while rewriting with replacing E with H. And this is about the two equations what we got from the basic formula. Now let us continue. As we know that the first Maxwell equation, we have solved this one and we got the equation. Then what you have to do here is that you try to solve left hand side and try to solve right hand side and equate it. Yes, I have done a LHS here. Here I can say that this can be written as like this. As you know, you have understood mathematics, but we have to take a reference as dou by dou z is equal to minus gamma. So instead of this dou by dou z, you replace with minus gamma, and it is a determinant. So try to solve the determinant, as you know your mathematical concepts, that how to solve the determinant matrix. Now once you got the determinant matrix of left side, let us take right side also. Now this is nothing but your left side. I have written over here the right side. Instead of E, I am going to represent in terms of unit vector I, J and K. So now E can be represented as IEX plus JEY plus KEZ. So now you have to equate the vectors or equate the equation with following unit vectors. So now I can say that here I can say that this I and this I can be equated, and we get this equation. For this three equation, let me explain the first equation thoroughly. So now j omega epsilon Ex is equated with I term, that is dou by dou y Hz plus gamma into Hy. So similarly you can go for second equation, third equation. Now the next thing what you have to understand is that let us consider equation 1. Our target is to find Ex, Ey, Ez, that you have to remember. Now we have to find Ex. For that what I have taken the first equation as a reference. Now Ex is written in this fashion also. Now here the basic concept to be understand is that Ex should be represented in Hz and Ez. But here Sz is there but not Ez. So how to solve Ez? For that you have to find Hy. So now the question is that how to find Hy. Again you have to take the Maxwell second equation. Again you have to apply del cross E as a determinant. Again you have to represent with the unit vectors. Then you have to equate. Then you can get Hy. So instead of writing all these things, I have written Hy directly for my convenience. So now I can say that once you solve this one, you can obtain Hy. So now this Hy can be substituted over here. Yes, we are showing the interest to find only Ex, not remaining thing. Once we find Ex, we can find remaining also. Now what I have done is that Ex is nothing but Hz. I have to substitute Hy. I have substituted Hy. I have solved mathematically. Please check once, and in doubt you can clarify with me. So I think that it's maximum you are going to get the clarity because I have written step by step. Now what we have done is that we got Ex, and we know that this is nothing but your H square. So we got Ex. Now I can say that Ex in terms of Hz and Ez, and this is your finalized equation. So always you should say that Ex should be represented in Hz and Ez because this is the direction of propagation. Similarly, you can find Ey, Hx, Hy, but the point to be observed here is that it should be represented in terms of Hz and Ez. So now I can say that Ey, Hx, Hy is represented in terms of Hz and Ez, and this is nothing but your Field's equation. So for the conclusion, I can say that you have taken the basic wave equation, then you have taken the Maxwell 2 equations, you have solved this one, and then